right? So we are going to do mathematical modeling. So before this, we should know that what is mathematical model and why we are doing this mathematical modeling. Suppose we have this original setup, the experimental setup, original physical system, or the experimental setup, and suppose here we have gotten some mathematical correlation here, and we have an input, and suppose the same input is being applied to both. This is the input, and here we are getting one output from experimental setup, and suppose from mathematical correlation also we are getting some output. So if this should be arrow, so if these two outputs are close enough, then we will say that this mathematical correlation is a good representation of this experimental setup, right? So a mathematical model will be a representation of a process of a plant, right? So that we can have a better understanding about the process, right? So in this, if these two outputs are close enough, then we can say that this mathematical model is representing that particular physical system satisfactorily, right? So the first point you said that if we have a mathematical model, we can understand or we can analyze the system behavior, right? So yes. So if we have a mathematical model, right? So as we have drawn here, if we have a mathematical model, so we can easily analyze for a certain input. Suppose we are applying a step input, then what will be the response? We are applying, suppose, some other input, ramp input, or some other input. So what will be the response? So these analysis can be done easily before actually doing it on experimental setup, right? So we can have, so this is one of the benefit of having mathematical model, that we can see the behavior of a physical system if the mathematical model is representing closely, right? So we can have we can analyze the behavior of that particular system without applying the inputs to the actual setup, right? So we can apply this on mathematical model and we can see the behavior. So this is one of the major advantage of having mathematical model, right? We can see the transient response, we can see the steady state response or other things, how much oscillations are there and in how much time it is being settled down. So all these things we can analyze if we have a mathematical model, right? The second thing is that operator training. So the person who are responsible for the operation of the plant, we say them operators, plant operators or the process operators. So a plant operator can be trained without performing this, without applying the inputs or without using experimental setup, right? So the operators can be trained via simulators, right? So I have heard of when I was learning driving, somebody told me that you can go to the Maruti driving their center, and they have they first they train the people on some simulator, right? So you don't have to actually drive a car, but there will be a simulator, and you will be feeling that you are driving a car, right? So then after you will be good enough in that simulator, then they will give you the actual car, right? So same type of simulators we can use for training of operators, right? We can train those operators on a particular plant without going to the actual plant in the same fashion, right? So the process operators can learn that suppose there is a tank or suppose there is a process. So they can apply, they can increase the inputs, they can decrease the inputs, and they can see that what is the limitation of this particular valve, what is the limitation of this particular tank, how much pressure it can withstand or how much temperature it can withstand, right? So before experiencing these things on actual setup, they can use the simulators, right? So we can use simulators if we have a mathematical model. So we can design simulators, and operators, the plant operators can be trained so that they can operate the plant, the actual plant, in a better way, right? So this is the second point. We can have the operator trained in if we have a mathematical model. Third thing is that obviously we can have yeah, process design, right? So if we have simulated a plant, right? If we know the limitations of design of a particular tank, suppose, so using simulations we can have that information that this particular tank, suppose we have to design a tank, we have to design a reactor, so we can have that information that how much pressure this tank or reactor or how much temperature this tank or reactor can handle, right? So the mathematical model also helps in design of process, design of plant. Okay, so this was the second point. So the process model can be used to design the chemical equipments, right? So that we can have a desired production rate, desired product of desired quality, right? We can have an idea about the size or the materials or the dimension of the tanks or the reactors. Okay, so the mathematical model can be used for design of process. The same, these things can be said under safety, right? So we have seen that how safety is required, why safety is required in process control. So to design a safe plant using all the safety measures, safety precautions, mathematical model or the process models can also be used to design safety systems, right? So for design of wall, for design of tanks, in with respect to some temperature, pressure. Okay, so a mathematical model can be used for safety purpose also, for process control also. Obviously, if we have mathematical model, we can simulate or we can design a particular whether feedback will be suitable, whether feed forward will be suitable for that particular plant, and how we can handle the temperature of the tank or the pressure of the tank or flow rate of the tank, flow rate of the inlet, outlet. So all these process control designs we can perform if we have suppose more than, we have seen only one tank, right? So if we have suppose 50 tanks or the 100 tanks, right? So there will be 100 variables, 100 disturbances, right? So in these cases, in a complex plant, so if we have mathematical models, so design of process control would be easier. So that is why we need mathematical model. Other than this, there could be some other points like if we have mathematical model, so we can identify or we can select the control variable and manipulated variable pairs for the control design, right? So for the selection of control variable and manipulated variable, we need mathematical model. Only then we can have a better idea that using this manipulated variable, we can control this particular output variable or this particular control variable. Okay. To understand the big process behavior, for training of the operators, for process design, safety, process control, selection of controlled variable and manipulated variable pairs, right? And there are some controllers to design model-based controllers. There are many controllers which is based on the mathematical model. Without mathematical model, you cannot design those controllers like internal model control. So internal model control is one of the controller design methods in which you need mathematical model, right? So for many cases, for design of controllers also, we need mathematical model, right? And the last thing we can say that to optimize the process operating conditions. Okay. So the purpose of the plant, any process plant, is to have profit through the products, right? So to have most profitable environment or the operating conditions, we need a mathematical model so that we can have all these things, design, safety, and other things. We can have an economical and profitable plant, right? So if we have a mathematical model, we can optimize the process operating condition, considering all the criteria, safety or the operational constraints and environmental constraints and all other things, right? So these are the few points that why we need mathematical model.
Thanks for watching. Master Control. Master the future.